Chapter 27 notes. This is a cathode ray tube, and the early part of the 1900s, it allowed us to make a lot of great advances in the field of physics. At this end is something we should be familiar with. We have two parallel plates. We have electron on the negative plate storing potential energy, and we let go. It comes flying out here at an amazing speed, and it hits the end of our cathode ray tube, which is coated with phosphorus material that glows when it's struck by electrons. Around the center of the tube, we have a coil of wire with electricity going in this clockwise direction. And my first question about that is, what is the direction of B? So we're going to use the loop rule. I'm going to put my fingers in the loop with my thumb in the direction of the current going clockwise, and my fingers are going into the page. So my field is going into the page from that loop. Second question, what will be the direction of the force on the electron? I now have a moving charged particle moving through a magnetic field. So we're going to use the left-hand rule because it is an electron. And I want to start off with my hand in the direction of the electron moving to the right, and I need to cross it into the board, so I'm going to have to rotate my hand around, so I'm crossing into the board, and that makes the force going downwards. So if I send that electron out, it has a downwards force, and it moves down and hits the bottom side of the cathode ray tube. Next, I'm going to take away that current, and I'm going to turn on, I have two parallel plates, positive plate on the top, negative plate on the bottom. And my question will be, what is the direction of the electric field? Remember, electric field goes from plus to minus. So the electric field in between these plates, they're all parallel going downwards from plus to minus. Question 4, what is the direction of the force on the electron? As the electron goes through this electric field, it's also going to feel the force. It's going to be attracted towards the positives and repelled from the negative, so it will have a net upward force on it. So as it goes through, it gets bent upwards. So if I turn both of these on at the same time and get them balanced out just right, our electron goes right through the center. And this is what they were able to do in the early part of the 1900s when we were studying this. From the cathode ray tube, we know that our two forces, the magnetic force and the electric force, are balancing each other. If we put those two formulas together, the charge cancels out, and we have a relationship of E to B for the velocity of the electron going through the tube. Around the same time, we were also experimenting with a device called a mass spectrometer. And in this one, we have a charged particle that comes shooting out into another magnetic field again. And as the electron hits the field, it feels a force towards the center, and thus does a circle around the center of that force. Remember, anything going in a circle has a force going towards the center of that circle. From this piece of equipment, we can put together our two forces. The magnetic force is becoming a centripetal force. So I put those two formulas together, and it gives me this relationship. And what they were able to manage from this is I could rearrange this to find the ratio of the charge to the mass in terms of the speed, the field, and the radius. And from what I know with the cathode ray tube, I can substitute my V is E over B, and we come up with this relationship that tells the charge to mass ratio. Then came along Millikan, and remember Millikan's oil drop experiment, he found out what Q was, and this was such a big deal because not only did we get the charge of the electron, but now we were able to go back and use that same equation to figure out what the mass of the electron was. So this was a huge step forward in the early 1900s. Right, our next topic is Wien's law. Black body radiation. All objects give off radiation, either heat, infrared, or light, depending on its temperature. This is Wien's law's formula. The wavelength of the radiation that you give off is a constant divided by the temperature. It's inversely proportional to the temperature. This formula answers the questions, why does something glow when it's red hot? What is the color of a star? Or what is the color of a blowtorch? How does a filament of a light bulb glow? So look at some sample problems. What wavelength do you give off? Every object gives off radiation. So we'll start with the body temperature of a human's 35 degrees, and for this formula your temperatures need to be in Kelvin, so we change it to Kelvin by adding 273, and then we put in the formula. Notice the units had kelvins in it. My kelvins cancel out, and we get meters. 10 to the minus 6 meters is micrometers. So this is the wavelength that we are giving off as humans at 35 degrees. So what wavelength is that? Things in the micrometer range are infrared. We give off infrared, which we perceive as heat. So let's look at the sun. We can figure out the temperature of the sun looking at the color from it. The average color of the sun is 590 nanometers. That's the yellow light coming from it. So I took Wayne's law formula and rearranged it for temperature. So this time I'm dividing by the wavelength. And the meters cancel out, and we have a temperature in kelvins. It's almost 5,000 degrees Kelvin is the average temperature of the sun. Now this is a graph that also comes along with Wayne's law, and it's showing the output of the sun, and you can see the main output of the sun is down here in the visible light. Most of what comes from the sun is visible light. This portion of the graph is showing that it also gives off infrared, and this portion of the graph is showing the sun also gives off ultraviolet light, but the majority of it is peaking in the visible light spectrum. So what is a black body? I know that black shirts absorb sunlight. If I go outside on a summer day, I'm going to get warmer than if I'm wearing a white shirt. And that's kind of what leads us into this black body. It is an imaginary object that absorbs all of the wavelengths of radiation that shine on it, like a black shirt absorbs heat and light and other radiation, and it gives off radiation according to Wayne's law. Next topic is Planck's quantum hypothesis. He said that vibrational energy of molecules in a radiating object is quantized with this energy, and actually gave a formula to it. Now, quantized means it only exists in certain discrete amounts is the word they use. It's just certain amounts. For his formula, n is a whole number integer, h is Planck's constant. There's two versions of it on your formula sheet. One is for joules and one is for electron volts. These are both units of energy, and on the back side of your formula sheet, along with the constants, there's a conversion to change joules into electron volts. And by giving you two constants, it just saves you that step of having to convert. You can just use the other constant if you need it. And of course, F is the frequency of our vibrations. So let me show you what we're talking about. And this is a model I made of a carbon dioxide molecule, and I'm going to add some energy to it. Some high frequency energy didn't seem to do much to it. If I add low frequency energy to it, still doesn't seem to do anything. But if I find just the right frequency, I can get it to vibrate and keep vibrating. And this is what Planck was noticing, that just a certain discrete amount of energy would cause that vibration. These are the same vibrations that are causing our global warming issues and the greenhouse effect. Greenhouse effect, I always see these weird diagrams where light comes in but can't get out of a glass house, or light comes into the earth and does all these weird bendy things. It never really made sense to me until I started looking at it in terms of the physics of what's going on. Look at this one. The light rays come in and they bounce up and down in between our atmosphere. So this is a model of our atmosphere. Our gases are oxygen and nitrogen and carbon dioxide. And so what I've done is taken away the oxygen and nitrogen, and we're just looking at carbon dioxide molecules. Now, we said that the sun gives off mostly light rays, and those light rays don't do anything with the carbon dioxide molecules. The sun gives off ultraviolet rays, which also does nothing for the carbon dioxide molecules. But the infrared rays, those molecules will absorb that energy and start vibrating, as I had just showed you. And they vibrate for some random amount of time. It could be a couple seconds, it could be a couple hours, or it could be up to half of a day even. And when they stop vibrating, they give off that same frequency of energy, and some other molecule will absorb it. And that energy gets passed around from molecule to molecule to molecule, and eventually it will be given off back into outer space. And the concern with our global warming is if we have too many of these molecules, we're going to trap that heat in for too long of a time and heat up our atmosphere unnecessarily. So this is a better drawing that I actually found. not only does these carbon dioxide molecules absorb the heat rays, the infrared rays from the sun, but the Earth acts like a black body. It absorbs the light rays from the sun, and because the Earth has a temperature, it will give off infrared radiation just as people give off infrared radiation. That's the heat waves that come off of us. And those heat waves also get absorbed by the carbon dioxide molecules and get trapped in our atmosphere for a random amount of time before they're finally given off. Now, all of this trapping in the heat is very good. At the nighttime, when the sun is not out, we need this heat trapped in our atmosphere to keep us warm at night. So this whole greenhouse effect is actually a very good thing. The concern is that if we have too many molecules of greenhouse gases absorbing too much heat, it can heat up the Earth over a long period of time. So Einstein claimed that the light given off is also existing in the same small discrete quantities that he called photons. Next topic is the photoelectric effect. Basically, we're shining light onto the surface of a metal, and that can eject electrons. Now, this is a huge thing. It shows that light acts like a particle, and it proves Einstein's quantized theory. These are particle collisions. This photon has momentum, and that momentum is being transferred to an electron. So this is very important because it is showing that light acts like a particle. So we can use the photoelectric effect in our solar cells, such as the ones in our calculators. So let me show a little experiment. I'm going to shine different colors of light onto the solar cell of the calculator, and you should have the wavelengths of light memorized. 700 is red, and 400 nanometers will be our violet light. I'm going to start over at this end of the spectrum with red light, shine it onto my calculator, and nothing happens. I'll scoot over to orange. Nothing happens. Scoot over to green. Again, nothing happens. Scoot over to a lighter blue. And suddenly the calculator turns on. Scooting over to a darker blue. Still get the calculator to turn on. Going on to violet, the light also comes on. So I'm going to take Planck's formula, and usually when we use this formula, there's no n. We just ignore the n. And Planck's formula is looking at the energy that's coming from the light that we're turning into our electrical energy here. It's Planck's constant and the frequency. Now these numbers are wavelengths, so we're going to do a little trick here. I'm going to take the speed formula for a wave. All of these waves travel at the speed of light. That equals wavelength times frequency. So I'm going to solve for frequency and substitute in place of the frequency. So this is Planck's formula just in terms of wavelength instead of in frequency. Looking at this, we can see that a larger wavelength is going to give me a smaller amount of energy. And down here, a smaller wavelength is going to give me a larger amount of energy. Somewhere in this blue range, there's a threshold frequency where suddenly we can eject electrons to create electric current, where over here we did not have that energy. And that threshold is called the work function. The work function is the minimum amount of energy needed to eject the electrons from our light. So this is the formula for the photoelectric effect, and it is just the conservation of energy. This is the energy of the photon. This is Planck's formula, E equals hf. And on this side, this is the kinetic energy of the photons that are coming out, and this is the minimum energy required, the work function, to release our electrons. This is a graph. We took the formula and rearranged it for kinetic energy. And you can see on the graph, the intercept down here is the work function. The slope is Planck's constant, and it's just a graph of kinetic energy versus frequency. So this shows the x-intercept is the threshold frequency, the minimum color of light that would allow electrons to escape. And down here, the work function is the minimum energy needed to eject those electrons. So these are the new formulas for the chapter. This is the photoelectric effect. This is Planck's formula. These two came from Einstein. Einstein said that photons have a momentum even though they don't have a mass, and that momentum times the speed of light happens to be that same energy. Later on we'll get more into the E equals mc squared formula and what that means. This formula is a topic for our next notes, but I'll have you go ahead and copy it down right now.